Okay, good morning, everyone. I'm Damon Teagle. I'm chair of the program advisory group that runs the UK involvement in scientific ocean drilling. And I just want to welcome you to this meeting today, where we're going to be concentrating on mission-specific platforms over the next couple of days. Before I go on with this, I just want to really thank all the people involved in putting this workshop together, and their names are listed on the bottom of the slide here, but in particular Dave McElroy and of course Jude Coggin. So Dave McElroy from BGS, the European Science Operator, and Jude Coggin, who's the UK IODP Knowledge Exchange Fellow, who's done all the hard work actually putting this meeting together. So what are we going to try and do today? Well, this is the fourth one of these proposal training exercises that we've run in the UK in the last decade or so. The last one that maybe some of you took part in was in September 2018, and we hosted that in Southampton. And of course, this experience is going to be a bit different. We haven't done this online before, so we'll just have to see how that goes. But the key to this is really for the people involved in the workshop and in the proposal development part is really, make some time over the next couple of days and engage in this, because you'll get a lot more out of it. It'll be more fun for all of us, and hopefully some really good ideas will come out, mature, and develop potentially into fully fledged drilling proposals. So what are we going to do over the next couple of days? We're going to introduce you briefly to scientific ocean drilling and the current phase of the International Ocean Discovery Program. And of course, I hope many of you got to see the excellent primer talks we had last week from various parts of the European Science Operator. We'll also want to just highlight the opportunities for many of us taking part in scientific ocean drilling expeditions, either on mission-specific platforms or on the Teagle or on JR, have really been career-building opportunities, and the international relationships that we've developed through those have been very important for our careers. The structure of scientific ocean drilling can, for some people, seem quite mysterious, and actually it's not. The key to scientific ocean drilling has actually always been that it is a bottom-up, community-led, proposal-driven system. But we will do our best to try and introduce you to the system and how things are evaluated. Once again, the strength and why scientific ocean drilling has been successful for so many decades now has been that it is proposal-led and there is a transparent peer review system. And then the teams of participants are going to be helped, but they're going to take leadership in preparing a proposal for future mission-specific scientific ocean drilling. Previously in these workshops, we haven't emphasized mission-specific ocean drilling, and it wasn't, but as you'll see, due to the likelihood of the way that the scientific ocean drilling will evolve over the next decade, we really think it's timely that we really spend some effort and concentrate on the opportunities of mission-specific scientific ocean drilling. Okay, so what are we going to do over the next few days? There will be a team exercise, and that team exercise will be to develop a hypothetical scientific ocean drilling proposal. We want that targeted towards a mission-specific platform, and then there'll be a couple of rounds where that team will present both initially a pre-proposal and then a full proposal to a interdisciplinary panel of experts for evaluation and feedback. And at the end, we will choose one or perhaps more for virtual scheduling. So how's this going to work? You'll work in teams of about 6 with various mentors and specialists, and we will develop a pre-proposal, which will be in the form of a short PowerPoint presentation, and there'll be a team presentation 2 p.m. Wednesday, so that's tomorrow, remember, at least Wednesday UK, 2 p.m. Wednesday UK time. We'll give you some feedback and commentary. And then on Thursday afternoon, there will be slightly longer team presentations of the full proposal. So, the challenge is, and effectively, 50-something hours or so, is to take a very nascent idea and put that forward as a proposal. So the pressure is on. Just briefly go through the outline of what we're going to do today. Last week, hopefully everyone got the chance to see, and these are online if you haven't, the pre-workshop primer proposals about mission-specific platforms and different coring technologies, also the wireline capabilities, and how the cores get analyzed and curated for mission-specific platform. And then there was also an introduction to the new British icebreaker, the Sir David Attenborough. Right, today will just be some general introductions from me, and then some talk about scientific ocean drilling, and then that will be followed up by Ros Coggan, who will talk about the new scientific ocean drilling science framework, which is a recently released document that takes a future look out to 2050. Then a couple of highlight talks from Joe Morgan on the Chicxulub drilling, and Heiko Pelliker from talking about the Arctic, which of course was the first mission-specific platform drilling back in the early 2000s. And then after lunch, we will have the first of our group sessions when you'll get together with your groups and we'll start introducing you to these tasks. In purple there, you can see there's the afternoon is broken up into some other information talks, and then there'll be a second group session at about 3:30. The final talk about site survey requirements at 5:30. I mean, apologies for these long days, but it's really the only way that we can get this concentrated into 3 days. We did try and do this, sort out a schedule for a 2-day workshop, but it really just didn't give the participants enough time to develop the proposals. And then tomorrow, once again, there'll be some talks give examples of recent and upcoming mission-specific platform experiments, including Corinth and Japan Trench and Tahiti, from various colleagues from around the world. And then this is sort of the main highlight in red here. These are the sessions where the teams will be presenting their presentations about their proposed proposal. And that will be both the presentation, but also feedback from the mentors and other experts in these areas. And then Thursday afternoon, so there'll be more sessions to work on this on Thursday morning, and then the presentations on Thursday afternoon. When we've done this in person, there's been, of course, these sessions and the ends of these long days have been broken up with drinks and fancy dinners and such like. So it's a shame that we can't do that. Part of this is just to bring a whole bunch of young, enthusiastic scientists together to share their ideas It's a bit more difficult over the internet, but hopefully it'll still be a valuable experience. Now, we've taken your applications and very roughly clustered you into groups of similar and complementary skills. The matches are not exact, and in some ways that, and in many ways that doesn't matter, because many, if not most, successful IODP proposals have a very strong multidisciplinary component to them. There were a number of people who had some quite advanced ideas, and we've chosen 6 of those. Apologies if your idea didn't get selected, but we've chosen 6 of those as titles for these different teams. So please have a look around to see which team you're in. And you can see color-coded by Jude, also the mentors for each of those teams: Heiko, Ros, Tom Dunkley-Jones, Lisa McNeil, Steve Bahati, and Tony Morris. Okay, so these are initial ideas, these titles here, that came from what was proposed when people applied to this workshop. And but these ideas hopefully will evolve and will be refined, but they're general subject areas to just initiate discussions. So again, so just please note which group you're in, because when we move into the breakout sessions, you'll need to know where to go. So I think Jude will explain that in time. In addition to these groups and their mentors, there are a number of other specialists who will provide information on site survey requirements, sort of safety and environmental pollution, wireline logging and physical properties, the different platforms. Dave McElroy can provide specialist information on that, but many others can also help with that. Heiko and Steve Bahati, information on stratigraphy, Tony Morris on paleomagnetism, numerous people, but including Ros and myself on geochemistry, and a colleague, Jason Sylvan from Texas A&M, will be joining us through at times during the meeting, and he can talk in more detail about microbiology. Ros and I can also, and others can talk about different styles of seafloor installations. What I wanted to do just now, though, was just briefly talk about scientific ocean drilling and to a certain extent, the history of scientific ocean drilling and where we've come from. Okay, and some of these slides gratuitously stolen from Tony Morris, who's the ESAC chair at the moment. And here's a wonderful picture of the bow of Geordie's Resolution. So this is the main non-riser workhorse of scientific ocean drilling, sitting in remarkably calm seas. Not sure where though. Because the key point is something that as geologists and earth scientists, you don't need to be told, but maybe many of us forget, is that we live on an oceanic world. We can make hemispheric images of the planet where we basically can see very little land and almost no continents. Places like the Pacific Ocean are really, really large. Okay, so the oceans cover more than 70% of our planet. And of course, because of sedimentation processes and because of the general youth of the oceans also provide amazing records of the tectonic and climatic processes of our planet over at least the last 200 million years, and very high resolution records of the last 60 to 100 million years. Just from the bathymetry of the ocean, we can see many of the processes, or the products of many of the processes of plate tectonics, from the deep ridges and the mountain chains to the underwater seamount chains of hotspot volcanoes, through the large major fracture zones we see running across the Pacific to the mid-ocean ridges. And also there are areas of deep sedimentation that provide these high resolution records of past oceans and past climate. But although these sorts of maps of the oceans look quite detailed, in reality, they are really very sort of blurry images. And of course, these high resolution maps, such as this one here of the ocean floor, are relatively recent. You know, the Sandwell and Smith satellite-based gravity map of the sea floor is only from the mid-90s. And of course, these approaches only provide us with a resolution of somewhere around 3 to 10 kilometers of the sea floor. So really, this is actually a very blurry image of our planet. In contrast, if we went to the far side of the moon, which is seeing recent activities and landing of spacecraft, here's a topographic map of the far side of the moon, so the side that we never see. And from satellite altimetry, and because of the lack of water on the moon, there is a resolution of about 100 meters. So many orders of magnitude more detailed than the view of our own planet. Now, does this matter? Well, just to take an extreme example of a nuclear submarine, well, yes, it does. Here is the bow of a Los Angeles class nuclear submarine, USS San Francisco, from 2005, where in about 160 meters of water, this large multi-billion dollar nuclear submarine crashed into a seamount that apparently was not known about, and certainly didn't register on the United States Navy charts. Now this injured almost 100 people and killed one of the sailors, and the subsequent refit cost almost $100 million to fix. But here, you know, we have a situation where an organization that you might think is one of the best informed in the world about the bathymetry of the oceans is driving one of its prized assets into an unknown mountain. Okay, so our knowledge of the seafloor really is important and is still work in progress. Now, the older amongst you might shudder at these pictures, but it is really not that long ago that our knowledge of the oceans, before we had the framework of plate tectonics, was very different to what it is now. And I just show some pictures of this concept of a geosyncline. And if we go back 60 years or so, many geologists didn't believe in lateral movement of plates. It was not the established paradigm. And they thought that although there might be vertical movements, effectively the continents and sediments were just built up in huge piles called geosynclines. And the question was, well, if you drilled into a geosyncline or drilled into a big pile of sediments, would you actually go through the whole history of the Earth? Now, these concepts seem rather ludicrous these days, but of course, before there was plate tectonics, there was no intellectual framework to think about how the Earth was, how the Earth operated. And the right-hand picture here is one from Willard Bascom's very famous book called A Hole in the Bottom of the Sea, which is about Project Mohole, and Willard Bascom was sort of the chief engineer of Project Mohole. And this is just sort of showing a hypothetical view of the ocean crust. And just noting here, it sort of says sediments. Well, that's reasonable. Then they're not really quite sure whether layer 2, seismic layer 2, is basalt or maybe some sort of fairly well indurated limestones. The only information they have is from very shallow cores, maybe less than only 10 to 15 meters long, and some rather patchy seismic experiments. And then they think, or they feel, that maybe the deeper layer of the ocean crust is basalt, but there's a comment here, a matter of tradition rather than evidence. Was it basalt? Was it sediment? Was it gabbro? Was it something else? And then they've got the transition zone into the mantle that they don't really know whether it's peridotite or eclogite or dunite. Now, many of these thoughts actually existed probably into the career of certainly of many of the older scientists here. And I remember when I was doing my degree in New Zealand, my third year, we had this question, and a rather delightful exam question from our professors. Every geologist has in their wardrobe a battered field uniform that is no longer of any use, but they are still unwilling to throw away. Discuss this statement with respect to the New Zealand geosyncline. So even in a country as tectonically and volcanically active as New Zealand, these lingering thoughts about sedimentation and ocean history being preserved in these mysterious objects called geosynclines, continued well into the 80s. And of course, the real problem with this was just the lack of knowledge about the ocean floor and ocean sediments. And that could not be resolved solely by geophysics or by shallow coring. And that led Harry Hess and a number of leading, principally American scientists, members of the National Academy, through a rather curious organization called the American Miscellaneous Society, to propose deep drilling into the oceans, and in particular trying to drill down to the mantle. And actually it's 60 years ago at the moment that the operations of Project Mohole were taking place in the Eastern Pacific between March and April 1961. And these scientists, led by Harry Hess, Walter Munk, and others, the planning, fueled by breakfast and wine, took a oil service barge, CUS 1. CUS stands for the Continental Union Superior and Shell oil barge. They mounted a derrick on it. This was an ex-landing ship tank from the Second World War. And Bascom and colleagues effectively invented dynamic positioning. Could they position a ship in the open ocean, drill into the seafloor, and importantly, re-enter a hole on the seafloor? This expedition is beautifully illustrated in Life magazine and written about by the author John Steinbeck, with these very sort of moody, wonderful photographs by Fitz Gorrow, who's known as the atomic photographer, because part of his other work was photographing many of the atomic bomb tests. So Project Mohole has sort of gone down in history as being a bit of a failure, but in fact, it did invent dynamic positioning. It did manage to re-enter holes in very deep water, more than 3,000 meters for the first time. It's worth remembering that the major petroleum industries were only working in relatively shallow water of tens to maybe at most 100 meters at this time. And the deepest hole drilled was about 183 meters, mostly through Miocene sediments. But the critical observation that came out of Project Mohole was that beneath that, there was fresh, relatively young, fresh basalt, and they recovered 14 meters of basalt. This here is a picture of a telegram. Now, that is an ancient means of electronic communication that maybe some of the people in the audience might remember. But this is a telegram from John F. Kennedy, President, congratulating the scientists of Mission Mohole in this historic landmark of our scientific and engineering progress. Now, this is a level of political recognition that scientists really experience these days. Perhaps actually the scientists involved in making vaccines at the moment are actually getting this level of scientific accolade. But this was, sort of describes the level of achievement that these first scientific ocean drilling operations of Project Moho actually achieved. It was worthy of the recognition of President Kennedy. Now, Project Moho, unfortunately, it was taken away from the scientists. It was then passed on to various corporations. A huge amount of money was then spent, and no more drilling was ever done. And it eventually collapsed and was actually closed down by a young senator called Donald Rumsfeld, who appears later in history. But what it had showed was the importance of drilling in the oceans. And that, of course, led to initially a number of scientific programs that have been continuous since 1968. Initially, the Deep Sea Drilling Project with the very famous vessel Glomar Challenger, and that many of our colleagues still involved in scientific ocean drilling sailed on. But also there was the recognition that the construction and operation of drill ships and platforms for scientific ocean drilling was beyond the capabilities of individual nations. And this is a very important step. And from about 1970, we had the international phase of ocean drilling. And since then, there has been international collaboration. Okay? And scientific ocean drilling has worked as an international consortium with different partners providing ships, but proposals and scientific parties coming from all over the world, or at least the member countries. So the Deep Sea Drilling Project ran to 83, the Ocean Drilling Program, then headed out of Texas rather than Scripps, and now using the refitted drill ship BP Sedco 471, renamed Joyde's Resolution, here appearing in grey, was the workhorse for the ocean drilling program. However, Joyde's Resolution although it's an incredibly capable ship and has been home to many of us for a significant portion of our lives, cannot operate everywhere. It cannot operate in very shallow water. It cannot operate in ice-covered seas, and it has difficulty drilling very, very young, hard, brittle rocks. It has difficulty drilling sands. So there were many scientific challenges that could not be addressed with this riserless drill ship. It can also not drill very, very deep holes. So in 2003, the Integrated Ocean Drilling Program was established and ran for 10 years. And this brought new capabilities. There was a refitted and rebuilt Joyde's Resolution, now appearing in blue. The Japanese also commissioned the colossal riser drill ship Chikyu. And although this has principally been used for drilling in subduction zones, the express aim of the Japanese Science Ministry is to use this ship to actually complete Project Moho and eventually drill into the mantle. And European partners came together to develop this concept of mission-specific platforms. And here is a picture of 3 icebreakers up near the North Pole on Expedition 302, the Vida Viking with a drilling platform on board, the Spanish icebreaker Odin, and in the distance, one of the large Russian nuclear-powered icebreakers taking high-resolution sedimentary cores from the sediments beneath the Arctic Ocean. 2013, So, IODP brought these new capabilities to scientific ocean drillings, and effectively the ability to recover high resolution marine records from very shallow to the deepest water, from polar seas, areas of hazard, in particular gas, locations of environmental sensitivity where you don't want to take a huge ship like the Resolution or Chikyu, want to be more nimble and more sensitive about operations. And of course, the mission-specific platforms provide a very large range of different options that can be purposed for the specific scientific task in hand. And this involves jack-up rigs and diamond coring and geotechnical vessels or wireline rock drills, all the techniques that were described by Dave McElroy and colleagues a week or so ago. I think there was also a intellectual change in scientific ocean drilling up till, for most of the first 20 years or so. The oceans were so unknown that we were very much in an exploration stage. We could pretty much put a hole anywhere in the oceans, in the deep oceans, and find something new. So as certainly the ocean drilling program evolved, it evolved to having much more hypothesis-driven science, but also we evolved in the capabilities of putting sensors and instrumentation onto the seafloor to provide very long-term records and continuous records of what was happening in terms of pore waters, in terms of microbial experiments, in terms of high-resolution seismics, by putting instruments actually in the seafloor and in time, and either having sensors with long-term recording on them, or actually having these observatories networked into submarine cables if possible. Okay, so we've moved sort of beyond the exploration phase to a phase where we can both get continuous observations, but also undertake active sedimentation. And this is useful for long-term monitoring of fluid flow and seismic hazards, but also by sampling and recording continuously the Earth, we start to get observations that allow us to make to increase our knowledge about some difficult to measure Earth parameters like permeability of the ocean crust or sediments or the strength of plates. It also allows us to do experimentation in situ conditions, in the fluid conditions, in the temperature conditions, in the pressure conditions of the deep oceans, and whether that's mineral reactions or microbial experiments. We also have the ability to interfere with seafloor, for example, sediments, to look at the stability of gas hydrates, or to test things like slope stability. So the first IODP lasted until 2013, and then since 2013 until a couple of years' time, we've been in the phase of the International Ocean Discovery Program. And you'll notice the absence of the word drilling in that. And this was a decision directly related to the Macondo Gulf of Mexico drilling disaster, when in certain parts, particularly in Washington, having a program with the word drilling in was regarded as not sensible. And the International Ocean Discovery Program, still called IODP, continued with this 3 drilling strategy capabilities of riserless drilling, mission-specific platforms, and riser drilling. And it involves, and it should be said, because we do have colleagues here from around the world, that the partners are not just the United States, Japan, and Europe. They also include China, Australia and New Zealand, India, Brazil, and Korea. Now, there's nothing quite like 2 months at sea to really get to know people and to learn their abilities and learn their scientific interests. And it has been this expedition mode of operating, whether it's on the JOIDES Resolution or CHICU or on mission-specific platforms, that really, is the greatest strength of this program. Having teams of people work together on a common endeavor, whether it's at sea or on land. And this has been recognized, and Nature, about 7 years ago, in an editorial celebrating IODP, has a statement, arguably the most successful international research collaboration ever. And that's not just because of the excellent science that's been done and the capabilities of the vessels, but it really is about this ethos of teams working together on a common problem. And it's this opportunity to take part in a scientific team that involves graduate students through to the most aged of professors that is the real strength of the program. Of course, either on the ships or in specialized containers on the mission-specific platforms or back in the core repository labs of in Bremen, you have these teams of people working in specialist laboratories with dedicated technical staff. So you might say, well, what has scientific ocean drilling actually done for me over the last 50 years? And this is just a set of cartoons put together by Ros Coggin a number of years ago, but it sort of illustrates what scientific ocean drilling has managed to achieve in the last 50 years. And apologies, I've probably left some important advances out. But leg 3 drilled across the southern Atlantic and effectively showed through showing that sediments at the bottom, just above the ocean crust, got older in a linear fashion, effectively provided important proof for plate tectonic theory. It's provided us with highly accurate geological timescales, around 50 million years. We've looked at the processes of the complex processes of continental breakup, gained new knowledge about about subduction zones and how earthquakes are generated there and the fluid flow events that occur. It's really invented the whole subject area of paleoclimatology, and of course increasingly this understanding of Earth's climate is used to project into the future. It's provided records of CO2 and surface temperature for the last 65 or longer million years. And this allows us to make comments about future warming and the sensitivity of the climate system to CO2 or doubling of CO2. We've also identified regions in the past when there have been very large excursions in climate. Very important work on the stability of ice sheets and their impact or potential impact on global climate and sea level. We've confirmed the layering of the ocean crust. There's still work to be done there. We worked on active hydrothermal systems and made very important intellectual contributions to the understanding of all sorts of ore deposits, and particularly the rapidity of how fast ore deposits formed. As we'll see later from Joe, very important, Joe Morgan, new understanding on the role of extraterrestrial impacts on the Earth system and mass extinctions. And last but not least, also discovered these microbial ecosystems that both survive in very, very deep sediments, but also in within hard rocks as well, with some microbes actually sort of feeding on glass. Now, a number of the highlights of the integrated ocean drilling program have of course come from these mission-specific platform experiments, and we'll hear examples of these and the key findings of a number of these over the next couple of days. These are giving us important information on past Arctic conditions, the nature of and rapidity of sea level rise, the beginnings of continental growth and extension, and serpentinization systems, and also the impacts of extraterrestrial bodies, and particularly around the KT boundary from the Chicxulub drilling in the Gulf of Mexico. Now, every decade or so, scientific ocean drilling, and this is a community effort, gets together to write what is generally called a science plan. And this book here, Illuminating Earth, Past, Present and Future, was the plan that a number of us in the audience were involved with writing for this period 2013 to 2023. And it's worth looking through these books as for inspiration, but I just wanted to make some points. These science plans are not recipes. They are snapshots in time, and for this particular one, the team that sort of pulled this together on behalf of many hundreds of scientists were asked to write up a limited number of actual challenges. But these are snapshots in times, and these are best thought of as living documents. They're not Bibles or cookbooks. Okay, and I think the key point is that the program has always been responsive to good science. And if you have good science that requires scientific ocean drilling, then any proposal can be considered, and if it's as good scientific groundings, is likely to be successful. Ros is going to talk about the new scientific framework that will come into effect in the next couple of years. This is a very ambitious document and looks towards mid-century to 2050. And one of the motivations, and so, there will be a new program post 2023. The planning for this is just starting, but it is promising, and it is likely to have many of the great components of the current IODP. It is likely to have a globally roaming non-riser vessel. Chiku will be operating, certainly for some parts of the next program, and there will be mission-specific opportunities. However, when a new JOIDES resolution type vessel will be available is unclear, and there could well be a hiatus of where there is no JR like vessel. Perhaps the JR, JOIDES resolution, will continue to operate, but it's becoming a very old ship and increasingly prone to breakdown. And of course, drill ships take a while to build or refit, so there could well be a period when there are no JR-like operations. So it does seem timely, and why we've concentrated this workshop on mission-specific platforms is to try and build up the quiver of opportunities and proposals for mission-specific operations. So also wanted to finish with this. This is just a quick summary of the proposal structure for scientific ocean drilling. This is not the official version. This is sort of a stripped down version of it. But the key point about this is that, and this is the greatest strength of scientific ocean drilling, is that it is a proposal driven system. Although there is a science plan, it is not set in stone, and that the strength of scientific ocean drilling has come from the fact that it is driven by proposals from the community rather than any top-down direction. And then the transparent and nurturing review by the science evaluation panels. Okay, this is the key strength and effectively opens up the door to all scientists, whether they're involved in marine geology or not, and actually any career stage of to write scientific ocean drilling proposals. And certainly in the last decade, we've seen a number of examples of young UK scientists writing and leading successful ocean drilling proposals. So there are some things to learn and some approaches to, best approaches to take, but writing a drilling proposal should not be regarded as an unachievable task. Okay, so what are we going to do in this workshop? And the key thing is to learn through drilling. There will be some lectures, there'll be examples of previous drilling proposals, previous drilling expeditions and their successes. But the key to this is going to be this team exercise in which you're going to develop a hypothetical scientific ocean drilling proposal and then present it for evaluation from so-called experts. You're going to work in teams of 6 with mentors, and then by tomorrow develop a short pre-proposal presentation with just a handful of slides, and then on Thursday a more thorough, building on that feedback, a more thorough proposal for presentation and evaluation on Thursday afternoon. So some top tips. The key with all proposals, but in particular scientific ocean drilling proposals, is to come up with compelling, important scientific questions that can only be addressed through scientific drilling. Just saying that you want to go to one of your favorite parts of the world to drill a hole because it would be useful generally isn't enough. You really need to explain why we need these cores, why we need these measurements, and why that science is important. It isn't always the case, but it is often the case that IODP expeditions are truly multidisciplinary, that they have other aspects that complement the primary aim. And so think about what secondary and tertiary, what other goals can be achieved through your drilling, but without interfering in accomplishing your primary goal. How are you going to prove to evaluators that your targets are actually where you say they are? What site survey requirements do you need? Do you already have the data? If you don't, what experiments, what geophysics will need to be done to show that your targets are where you think they are, and actually that they are within range of scientific ocean drilling? We want you to concentrate on the science and sort of showing that you can achieve your science with drilling, but still bear in mind that there could well be important natural hazards around where you're drilling, or particular environmental risks. If you want to go to a area of outstanding natural beauty or a World Heritage site to put a drill hole or run a drill rig, that will require extra thought and extra planning. If you're going to be drilling in particularly gassy sediments or a petroleum zone, what hazards will you need to deal with if that's your goal? Through discussions with the mentors, think about what sort of platform you might need and what coring technology is most appropriate for your science goals. We want you to concentrate on mission-specific operations, but there once again are a variety, there's a broad range of options there, and a number of different platforms and coring technologies could be used. Will you need something very specific or novel, either in terms of possibly, say, wireline tools or instrumentation to go on the sea floor, or a new sort of coring seafloor mud motor or something that doesn't exist yet, or a particular vessel that would need to be adapted because it's going into very unusual conditions, such as 100% ice cover, for example. And also, how does your science fit in with the 2050 framework? We're looking to the future, so we might as well fit it in with the new framework, but just bearing in mind that good science is always acceptable to the peer review sort of system. But most importantly, what are the compelling science questions that can only be addressed through scientific drilling?